Today we're going to be looking at the area under a curve again, but today we're going to actually relate it to something called a definite integral. And over the next few days we'll see that this is a way easier way of calculating the area between a curve and the x-axis. So a definite integral is defined like this. Alright, this is the definite integral part. And it's just a Riemann sum. So again, this should look familiar from the other day. The limit as n approaches infinity of the sum from 1 to n of the function at our evaluation points, c1, c2, so on. So this is just a lot like what we did the other day with that, except over here we've got our definite integral. Here's our lower bound, and our upper bound is our b. And this is the integrand. And this dx means what we're doing with respect to x. So again, we're going to start by relating the Riemann sum to this, or this definite integral to the Riemann sum, and then we're going to use our Riemann sum that we were doing the other day to figure out what this limit is, or we're going to use limits to evaluate the integral here. So the first step is to write this out kind of like we did the other day with our limit as n approaches infinity, and then we've got our sum, so sigma I equals 1 to n, and I'm just going to write the definition first. So our delta x, you might remember, would be our b minus a. So 1 minus 0 over n. So in this case, it's 1 over n. And our evaluation points are just our lower bound, which is 0, plus delta x, or I delta x, I mean. So we're going to do some substitution here, and we're going to have the limit as n approaches infinity, 1 to n, and then our function here is 2x. So we're going to put in our c of I, which is just I delta x. So we're going to do 2I delta x, and then that's times delta x again. So as we do this, we've got 2 times delta x, so that's 2 delta x squared, and then I'm doing the sum from 1 to n of my positive integers I. So with a little bit of substitution, we get 2, and then I get 1 over n squared, and then this just becomes my summation formula for the positive integers. And if you notice, these 2's cancel out, and I'm left with, I've got an n squared, and I've got n squared on the top, so when I do my limit, I'm just getting 1 for this. And later on, we'll see, later through the week, we'll see how this relates and how we can actually calculate this way easier. But we're going to do another one with the limits and Riemann sums. This time the function's a little bit more complicated, but it's still doable. Alright, let me make that a little bit. So it's still doable. We're still doing the exact same thing we did the other day with this sigma notation. 1 to n. In this case, my delta x is going to be going from 2 down to 0, so 2 minus 0 over n, so it's 2 over n this time. My CI, my evaluation points start at 0, and I add on an I delta x each time. So if I plug these things in to my original function as I'm doing my limit, I'm going to put this in for I, for x in my original function. So I get I delta x squared, and then minus 3 times delta x. And we can go ahead and, make this I squared and this delta x squared. And we can actually split the sigma up. Our summation can be split up. So here I've got I squared delta x squared, and then I got it times another delta x. So I can actually do I squared delta x cubed minus, and then this one would be 3 delta x. And that's all in my limit. So since I've got that split up, we can simplify this down even more. Delta x cubed can come out of the summation, so I'm going to have 2 over n cubed. My summation formula for I squared would be n plus 1, 2n plus 1 over 6. And then my second piece would be the limit as n approaches infinity. And then I got 3 delta x. So the 3 with the n becomes 3n. And my delta x is my 2 over n. And now we just got to check our limits. So on the bottom here I've got n cubed. On the top I got n. So that's n cubed. So I've got 2 to the third times 2 over 6 minus, and over here the n's actually cancel out, so I've got the limit of 3 times 2, which is just 6. So we got 2 to the third, which is 8, times 2, 16 over 6 minus 6. And if I change that to 6, I get 36 over 6, and I do 16 minus 36, which is negative 20 over 6, which reduces down to negative 10 thirds, which is my final answer. Alright, so we've got a couple of theorems here that will help us out when we go to look at our integrals. We can combine some things, we can split things up. So here, if I've got from an integral from a to b of 2 functions, a constant times the first function, plus d, which is another constant times the second function, I can actually split it up into 2 integrals, just like we did with summation and things like that. Likewise, if we can find a value in between a and b, we can split up from a to b into 2 integrals, one from a to c, one from c to b. The other thing that's kind of interesting here is that if I reverse my endpoints from a to b and go from b to a, it actually puts this negative sign out here and helps us reevaluate things just a little differently. So, write the given total area as an integral or sum of integrals. And here we're talking about the area above the x-axis and below 4 minus x squared for y. So the easiest thing to do to get started would be to get a graph of it. And if you make a graph of it, you'll see that it crosses at 2 and negative 2 and goes up to 4 and does this. And we're looking for this area in here. Alright, so we're looking for that area. So all we really need to do is write this as an integral. In this case, we got the integral from negative 2 to positive 2 because that's where we start and where we end. And we write our function 4 minus x squared, and we got to tell somebody that this is with respect to x that we're integrating, and it's that easy. Alright, so my advice would be to get a graph real quickly on Desmos, sketch it out on your paper, and then we can write it out. So again, same idea here, the given total area as the integral or sum of integrals. The reason why it's saying total is if I have some pieces below the x-axis and a piece above, I want to write that as a sum of integrals to get the total area, because this would be negative, this would be positive, and if they cancel each other out, you get 0. Sometimes we want that, sometimes we don't. In this case, it says the total area. So if one's negative, one's positive, we've got to take that into account. Now this example doesn't do that, but the sine function does fluctuate back and forth. In this case, from 0 to pi, the function actually is all above the x-axis, if we remember from trig before when we graph these. It goes up to 1 and comes back down. So we're really just looking for this area here. So we're going from 0 to pi of the sine of x dx for our area. So that's our integral that we need to write here. Again, sometimes there's going to be pieces below, sometimes there's pieces above that you have to combine, and that's where you're going to have to think a little bit harder, and it's going to be a little trickier to work out, but it's not too bad. Here we're putting these together as a single integral. So if you notice, this goes from 0 to 2, this one picks back up at 2 and goes to 3. So our total would be just from 0 to 3 of f of x dx. Again, nothing too shocking, hopefully. Shouldn't be too bad. That part should be really simple compared to doing the Riemann sums. And this is asking us to sketch the area. So again, first thing to do would be to start with the graph of the function. So start with this function and graph it, x squared minus x. And we're going between 1 and 2. So if we look between 1 and 2 on a graph, there's 1, there's 2. We're just going to be between these 2 points. Now, this graph happens to have an x-intercept at 1, and it goes up to the number 2. Kind of curves a little bit more than that. Let me fix that for you. And then we go down and we sketch that area because it's the area of the region bounded by the x-axis and this curve. So again, the key is sketch, get the graph on like Desmos, and then sketch it. Alright, so we've got some tools today where we can estimate a range of where the value of the area should lie. And that's what this integral mean value theorem is saying. So there's some function value that the integral that will tell us pretty much where the integral lies. So if I do 1 over the difference of b to a times the integral of the function, we can use this to estimate the value by doing this, where m is just the function at a and capital M is the function at b. And if we do that, we get a range between where the value of the integral should lie. So as we're doing this, we've got to do a few things. Number one, we need to know what b minus a is. So in this case, I take pi over 2 minus pi over 3, and hopefully you can see that's pi over 6. So that's a number that we need. We need to figure out 3 times the cosine of pi over 2 squared. Now this is the pi over 2 squared part, not cosine squared, so you got to pay attention to that. And then we got to do the pi over 3 squared. Now, so this is f at a is the pi over 3 part. This is f at b. And that will help us find our range. So if you remember, I do f at a times b minus a, and that's less than the value of the integral. And then that's less than or equal to, again, the function at b is that capital M on that last slide. So if I plug the stuff into here, we can get our range. So really, we got to take the cosine, and I went ahead and calculated these out. So this first one is 1.36 approximately. The second one is negative 2.34. So if I take negative 2.34 times pi over 6, because that comes from my b minus a, that's less than or equal to this integral value, and that's less than or equal to 1.36 times pi over 6. So if I multiply those out, I can actually figure out exactly where I'm between. So again, this first one becomes, so if I multiply it out, I get negative 1.23, and the second one is 0.72. So I'm somewhere between those two. If I do another example like this, it's the same thing. So I can start with b minus a, which in this case is 2 minus 0, so that's just 2. And then f at a would be f at 0. So I'm plugging a 0 into my function, so 2 times 0 squared plus 1. That gives me the square root of 1, which is 1. F at b is f at the number 2, which is 2 times 2 squared plus 1. If I do that, 2 squared is 4 times 2, 8, plus 1 is 9, square root of 9 is 3. This value is going to be somewhere between 1 times 2 and 3 times 2. So it's between 2 and 6. So between 2 and 6. And that gives us a way to estimate the value of the integral. So some of them, if we don't have a way to work it out yet, we can actually solve where it's between. So here's the homework. Ask questions.